So in the voltage regulation of transformer, everybody knows the formula, what is the voltage regulation and how the voltage regulation change when the load changes. So here we are doing over here that Vs, the secondary voltage is 230 volt ampere. Here we are dealing with the ampere 0 to 65.2 with the interval of 6.52. These are the parameters of the transformer that has been supplied to us. R equivalent, X equivalent, and all those stuff. And now we have to calculate the current. We have to calculate the current, right? Current in different power factor. You know there can be three kind of power factor, things in the power factor, whether the power factor is leading, whether the power factor is lagging, or whether the power factor is unity. Similarly, whenever the power factor is leading or lagging or unity, the current will change. The magnitude of the current will change. So here, as you see, the leading current, that is ampere into 0.8 plus j 0.6, as you can know that 0.8 and 0.6 are the equivalent resistance and equivalent impedance of the transformer. If a unity power factor is there is no need to do anything, just ampere. And if there is a lagging power factor is there, then it's 0.8 minus j 0.6, right? Then you have to calculate the BPA. BPA equal to Vs plus R equivalent I plus J into X equivalent I. VR, as we all know, the voltage regulation formula, BPA minus Vs divided by Vs. The primary voltage minus the secondary voltage divided by the secondary voltage. So now we have to plot. Now we have to plot these things. That is, we have to plot the voltage regulation. And here I have written the code for you. And as we run it, everybody can see the graph that voltage regulation versus the load. As the load increases, if the power factor is lagging, the voltage regulation is increasing. As the power factor is leading, the voltage regulation is decreasing over there. And in the unity power factor, the voltage regulation is somewhat in the middle level. Is it clear, everyone? Voltage regulation of the transformer, that is nothing but, see the formula in your textbook, that is primary voltage minus the secondary voltage divided by the primary voltage. That is the for a particular transformer, right? And here we are trying to find out the relative voltage regulation of the transformer with power factor. How to do that? Using R equivalent and X equivalent. Here E2 minus V2 by E2. So first we consider three different current in three different power factor. I leading, lagging, as well as unity. Then we find out the BPA. Then we find out the VR, the voltage regulation. Absolute term you are taking, absolute of E2 minus V2 divided by E2, right? So this is the voltage regulation of the transformer, and then we are plotting it. Once we plot it, as you can always see that as the load increases, the voltage regulation. This is the graph between load and voltage regulation of a transformer in different power factors. Any doubt regarding this? Refer to your prescribed textbook for the theoretical basis. I am here dealing with the implementation aspect and how to implement this thing in MATLAB or Simulink. Clear? Similarly, voltage regulation of transmission line also you can do, voltage regulation of alternators also you can do. Here I am doing the voltage regulation of the transformer only. Similarly, second one is the magnetizing current. All of you know what is a ideal transformer and what is a practical transformer. In the practical transformer, what we require in the practical transformer, we have a magnet in the equivalent circuit of a practical transformer. We have a magnetizing resistance, right? In that magnetizing resistance, it is for the losses, and here this line load. This is the load. What we are loading over here? Suppose in MATLAB, how you load a external file. Suppose you have a Excel file or any other file or any other external file which has data in it. How to do it? How to load it in MATLAB. For Excel, there is a different command, that is XLS read and XLS write. But I'm not going to do that. If your data is in .mat or .dat format, .mat and .dat format is widely used in MATLAB. So here you go load something, load a file. Just you need to write load. That file name, it should be on .dat format, right? Most widely used is .dat, .mat, right? What is this file has? What this file has? This file has two columns. One is MMF data, one is flux data, right? MMF is magnetomotive force. The magnetomotive force is in first column, whereas the flux is in the second column, right? Now, all the parameters are available over here. VM, maximum voltage, is 325. Why it is 325? It is 230 into √2. And P is 850. VM is maximum voltage is 230. And P is 600 primary turns. Right? Here the frequency is 60. You can also do it for a frequency 50. Omega equal to 2 pi f time flux equal to minus Vm divided by omega np into cos omega t, and again you will find MMF, and Im, the magnetizing current, is the MMF divided by the Np. Then you can find the IRMS and you can plot. Similarly, you can do it for a 50 Hz also. Let's run it and check it out. Then you can understand it. Here, the magnetizing current at 50 Hz. Magnetizing current at 50 Hz. As you can see, these are the non-linear magnetizing current. These are the non-linear magnetizing current. The magnetizing current should be ideally, practically, it should be a sinusoidal wave, but due to the transformer property, it is working as a this kind of waveform. You see the magnetizing current of a transformer at 50 Hz. Any doubt regarding this? Okay. Yesterday we saw the torque speed characteristics. You can always see the terminal characteristics and all. Yeah. Yes, simple codes. Do you require the code? Let me know. You can find this in the book called Chapman. It's a very good book for machine, right? And here the data are also provided. From the data you are plotting everything. Okay. Next step, a simple RLC circuit. I am showing it to you. Then we will go for the let's go for a simple power electronics, half wave, full wave, bridge rectifiers, and all this stuff. Go to the blank model. It's taking a lot of time, and let me show you something real quick. Technical issue over there. Yeah, coming. Here you can see the magnetic field. Let's put this. Okay, so go to Simscape, Power System, Specialized Technology, Fundamental Blocks, Power GUI. Then let's go for a simple rectifier circuit. Then we'll be moving on to more complicated circuit, power electronics and all. Simple half wave rectifier, or let's suppose a bridge rectifier, right? We have already done that bridge rectifier in that, and I will show you how to do it again. Take the source, go to AC voltage source, and go to universal bridge. Double click on it. Bridge arms are 2. It should be diodes. Okay. And here elements, go for a series RLC branch. double click over here, 50 hertz. So now we will be connecting voltage voltmeter and ammeters. Go to measurement, to ammeter and a voltmeter are both input side as well as the output side. Let's consider a RL load only for the timing. Right, go to sync, go to sync and source side as well as load side. If you are having two sinks, double click on it. Go to the setting, apply. Okay. Similarly, this one, scope, to layout, just change it, now run it. See over here, this is the current and this is the voltage waveform. Similarly, this is the source current and this is the source voltage and this is the source current. As you can see, the source current is non-sinusoidal in nature. You can find the TSD of the source current. Now here, if I make this load higher, make the inductive part of the load higher, ultimately you will get a square wave of the source current. You will definitely get a square wave of the source current. So suppose I increase it much higher, 15 millihenry, right? Here you can see whenever the inductance value is increased in the load, the source current is changing to changing to square wave in nature. What you can do over here, you can do Fourier analysis by going to log data, structure with time. Okay, double click on the continuous. We have discussed it previously also. Tools, FFT analysis, scope data input 2. This is the input 2. The frequency is 50. Display. Make it to harmonic order. Display. Now, as you can see, the odd harmonics over here are predominant in nature. That's why this is a nonlinear nature, nonlinear nature of the waveform. And the THD is also pretty high. THD is also pretty high. If you reduce this load current, if you reduce this load inductance of the load, then here you will get the somewhat non-sinusoidal nature of the source current. Input to Ricard harmonic order display. This is 11.34 TSD. So from this we conclude that as we increase the inductance of the load, the THD value also increases. THD value of the source current also increases. THD value of the source current means the odd harmonics are predominant. See over here, first harmonics, third harmonics, fifth harmonics, seventh harmonics, ninth harmonics, 11th, 13th, 15th, 17th, 19th, all these harmonics are predominant in nature. All right. Any doubt regarding this? This is the source current. This is we are analyzing the source current. Similarly, the load current is as usual. But as you increase the load inductance of the load value, the TSD of the source current also increases and all. Any doubt regarding this? So this is a bridge rectifier. Last time we, in spite of this load, we put a last class and the previous one class we have put a DC motor over here. and we analyze it. Today we are not putting a DC motor, we are just putting a RL load for a simplicity purpose, and this RL load we are changing the inductance value of the load and observing the source current and the THD, total harmonic distortion of the source current. Right? Let me know if any doubts are there so that we can move forward. Similarly, this is a single phase. Similarly, we can do it for a three phase also. Similarly, we can do it for a three phase also. This part will remain same as it is. This part will only change. Right? The source part will only change. So let's do it. Remove the source part. Go to Simscape. Electrical sources. Three phase sources. And do it as a 3. Okay. So as simple as connection, but in between that we need a measurement block. Measurement block are really essential. A to A, B to B, C to C. Similarly, A to A, B to B, C to C, BABC, IABC. Now let's run it. Let's see the okay, something went missing. Let's check what happened. Okay, not that much. We need 400 volt, 50 hertz. Still the voltage is not showing. Internal resistance is not required. Noisy connection. Okay. Yeah. Now all right. And here you get the output voltage as well as output current. Here also we can do the THD analysis over here. One by one. Tools. FFT analysis. Input 2. This is the input, second input. Display. According to the harmonic order. The third harmonic is expressed. First harmonic, fifth harmonic, seventh harmonics, 11th harmonics, 13th harmonics, all these harmonics are there. So close it down, and if we increase it, then see what is the outcome. Source side as well as the load side. Here, see the source side is also changing, and what about the load side? Load side is also, the current is also very much changing. So let's do again the THD analysis. This is input 2. start from, let's suppose 0.02 and display. Right over here, you can see that this is around 31%, same thing. First harmonic, fifth harmonic, seventh harmonic, 11th harmonic, 13th harmonic. These are the because diode has a non-linear VI characteristic, so it is termed as a non-linear device. Due to the presence of a non-linear device, it injects a non-linear current in the source. It extracts a non-linear current from the source so that it is shown over here. Clear? Any doubt regarding this? Obviously, also you can find out the power and power factor, everything from here. Any doubt regarding this so that we can move along? Or you can change it to Y only. Okay. Y. YN. Okay, wait a minute. YG, and here you can successfully make it to page to page. Here there is a page to page. As you can mark, as the inductance value is increasing, the output voltage is also getting smoothened out. Though the source current may not be smoothened out, the output voltage is getting smoothened out. For the output current to be get smoothened out, you have to increase the resistance. Okay. Still it is most no smoothened out, only the just a normal 100 ohms. It will do. And here is the input current and source current. Check the FFT. Input 2. It is much easier to analyze all this stuff in Simulink, and you can do your projects over here also in a very short manner. You can simulate any of the circuit and in a very short time and submit your projects over there with a lot of results a lot of graphs. That's why we are giving much emphasis on the use of MATLAB as well as Simulink over here, and students should know how to do it. Hands-on practice should be there. Okay. So this class we have started the power electronics, the basic rectifier circuits we have shown, the bridge rectifiers with a single phase source as well as the three phase source, and we have studied the source harmonics. Also, you can include source inductance over here, internal. Everything that over here you can include. And then also you can analyze these things. Yeah. What is the issue of what is the use of source in inductance or the effect of impedance in the source? This is the effect of impedance in the source. What you are doing over here is initially it was a YG, means delta G, delta ground type of source, three-phase source. Three-phase source connected in YG configuration, that is delta ground configuration. Now I am having a internal resistance of 0.8929 ohm, an internal inductance of source inductance of 16 millihenry, and the base voltage is always 25 kV. So the setup changes over here, and when I change it, the source, the nature of the waveform changes. The nature of the waveform changes because of the inbuilt resistance as well as the inductance, but there is a less change in your voltage as well as current, output voltage as well as the output current. Here, if you check the FFT analysis, this is the voltage. This always FFT analysis is done for the current part, harmonic order display. FFT analysis is again 24%. This way, by doing all this analysis, you can easily do some mini projects, and combining mini projects, you can do a major project. Right? No need to do, just sit 1 or 2 hours, do some simulation exercises, and whatever the results are coming, you can just copy it from MATLAB. MATLAB figure, you can copy it and paste it in your whatever your books, and finally you can complete your work, right? There are n number of possibilities that we can analyze. This I am giving some of the stuffs. Explaining some of the stuffs. Rectifier, I have given a three-phase rectifiers, single-phase rectifier, three-phase diode rectifiers only. These are uncontrolled rectifiers because the diode, you cannot control the forward biasing and the reverse biasing of the diode. That's why it is called a uncontrolled rectifier. Next class, if we are comfortable, we will go to controlled rectifiers. Controlled rectifiers in the terms of SCR and switches, thyristor families, right? If any doubt, let me know. Okay, do practice these things so that it will be easier for you to understand all this stuff. And you can always ask me doubt whenever you have any issues. And you can refer to your textbooks for the detailed theoretical analysis, right? Okay, thank you for coming. Now we will leave this meeting. Tomorrow we will, same time we will join again.